Okay, welcome back. So we are continuing our discussion on random processes, and we are starting with white noise process. White noise process. Let's say a process x of t is called white noise. Let me change this pen. If its mean value, let's say mean function, is equal to 0 and its autocorrelation is an impulse function, let's say, I will explain this further on. So what do I mean by this? Well, these two statements, its mean function is equal to 0 and its autocorrelation is an impulse function. So x of t, this is white noise, then this means the following, two conditions. Expected value of x of t is equal to 0 for all t, okay? In some cases, you may see that, the mean of this white noise process is also stated explicitly. There is a zero mean white noise process and so on. But in this course, when I say white noise, I will assume that its mean value is equal to 0, okay? How about this autocorrelation condition? Now, autocorrelation condition is, let's remember, Rx T1, T2. So this is the correlation of the sample at T1 and the sample at T2. If this is a complex valued process, it's a possibility, then the second argument is complex conjugated. Okay? Now, this is, let me write it like this, it's an impulse located at T1 is equal to T2, and its value is, let me write it like this, sigma W square, let's say T1, okay? Something like that. So what do I mean by this? If I sketch this autocorrelation function over here, so how can I sketch this? It has two, let's say, independent variables. And this autocorrelation function value, it will be in the z-axis, as you see over here. But what do I see is the following. So it's always equal to 0. So always equal to 0, unless T1 is equal to T2. So this is the line when T1 is equal to T2. Okay? So I'm on this plane. T1 is equal to T2. Okay. Now on this line I see impulses. Okay? But the weight of these impulses may change. Of course, for every point on this line, there is an impulse. Okay? Something like this. So why is the weight changing? So this is the weight of the impulse. Let's say this is T1 star. This is T1 star. Then the weight of this impulse will be sigma T1 star, and that's it. Just a brief note, in signal processing, when we talk about impulses, we sometimes use this kind of a notation, okay? For example, this is an impulse at T naught, so this means the following, 3, this is a function of time, T minus T naught. We don't say the amplitude of this impulse is 3, because this is not the amplitude, this is not an arbitrary function, okay? This is a generalized function, it's very specific. This 3 indicates that the area under this impulse, if you integrate it from minus infinity to infinity, or any interval containing this T naught, it will be, the area calculation will be 3. Okay, at the end you get this. So this denotes the weight of this impulse. So this is the reason that I'm calling this weights, but for the sake of drawing, for the sake of illustration, I'm drawing these impulses at different heights, just to illustrate that their weights are different. Their weights can change with respect to this. Okay, this is the definition of white noise. So let me give a special case. Let me write it over here. So stationary white noise, I will explain stationarity later on in more detail. But at this point, stationary white noise. So stationary white noise satisfies the following two conditions. Number one, expected value of x of t is equal to 0. Number two, Rx x t1, t2 is sigma w square t1, t2. Okay? So this means that I have both of them at the same time. Stationary white noise and vice versa. Okay, this is the definition. Okay, stationary white noise. So what is the difference? Now this is not a function of the arguments. Okay, it's a constant value. So you may say that this height drawing, they're at the same height, but height is not the proper word. They're at the same weight. Okay, they're at the same weight. This is called stationary white noise. I will explain this concept stationarity pretty soon. Okay. Now, what do I have? Well, if you think about this definition of the, okay, let's think about it further a little bit. Now, this correlation function tells us about the predictability of one sample over the other one in a linear sense, isn't it? We have discussed this in length many times. So what do I see? I see that white noise is a very special kind of process. If you move, let's say, from T1 by 0.00001 seconds away, then the process becomes uncorrelated. Okay? So you see that every sample, however it is close, every two samples, however they are close, they are uncorrelated. Okay? So this is very particular and very, let's say, striking for this process. And as you can imagine, the definition of this process is quite complicated in mathematics because, you know, this generalized function is appearing in the autocorrelation. And there is so much going on, but let's assume that we are happy with these kinds of definitions and we will be making use of them. Okay? So strict definition is quite complicated. So let me have some examples. Okay. But I hope that you appreciate the difficulty. If I deviate from T1 by, let's say, 1 microsecond, it says that it's not predictable, they are uncorrelated. Okay, it's not predictable in a linear sense. They are uncorrelated. These two samples are uncorrelated. So can you imagine a process like that changing very rapidly so that it becomes uncorrelated immediately if you move from this sample? This is the white noise process. Okay. Now, example. Let's see. Two random processes. X1k, these are discrete time processes, and X2k. What do I mean by discrete time processes? They are just the samples of maybe a continuous time process. Okay, I'm just sampling a random process. It becomes, of course, sampled process. Are given A, X1 of k, this is random process number 1, is equal to theta, where theta is Gaussian distributed with, let me see, n 0 0 sigma, let's say w square. Then let me call this w. Okay, this is a Gaussian random variable, and so on. B, x2 of k is w of k, where w of k is IID. So IID means independent and identically distributed. Okay, with 0 mean and sigma w square. Okay, so the question is, find PDF and moment description. First two moments, of course. Descriptions of these two processes. Okay. Okay, so how can I handle this? So let me divide this board into two. So this is for x1 of k is equal to w. This is second process, x2 of k is equal to w of k. So before starting this, solution, we should understand what is going on. So how can I, draw some realizations of these two processes? So this one is, well, it's a little interesting. I'm sampling something, but there is a sample space. From the sample space, a single draw has occurred, and that's from a Gaussian distributed, let me say, a bag. Okay, you are picking a quantity randomly from this kind of a distribution. So this is your famous sample space. Then at the end you have a number. Let's say that this number is 1.2. Then for every sample of this process, x1, let's say realization number 1. Let's say first realization. Okay. So it remains at 1.2 for all, as you see, samples. -1, -2. I think it's clear. This goes like this. Now, what is another outcome? Or what is, if I select another outcome from the sample space? Let's say that it is equal to 1.6. This is the blue one. It's a little taller. Okay. But what is important is that this process remains constant for all t. And of course, it can have negative values because it's coming from a Gaussian distribution and so on. So this is, as you see, goes on like this. Okay, so these three dots emphasize that this kind of structure goes on forever. How about this one? Now the second one is from the sample space. So this is the birth of this random process. So you may say that at the birth time, I am not given a single random quantity, but I am given infinitely many quantities over here. This is the parameters of this distribution, you may say. So, but what I see is that, at time 0, I have, for k is equal to 0, so this is a Gaussian distribution, sample from a Gaussian distribution, maybe it's something like that. At the next time, it's something else, something else. So again, black one is the first realization, let's say. So at the birth of this random process, I have infinitely many, let's say these samples, Gaussian samples, for the black realization, black colored realization, as you see. Okay, I'm just making this up, some random looking quantities, and black one goes like this, first realization. Now the second realization, let's say the blue one may be something like that. Okay, so again this goes like this. So what is the difference? So in this one, this process has a single, let's say, independent or degrees of freedom, you may say. So how can I define this process? By this number. But to define this process, I have to have infinitely many, an infinite length, let's say, vector. And that infinite length vector defines this process. Okay. So how do you get the values of that, elements of that infinite length vector? From this Gaussian distribution with IID sampling. Okay, that is the difference in between these two processes. Okay, now we have understood it, I guess. Now let's look at first order description. First order PDF description. So let's say x1 of, let's say I'm at k1. Okay, so and let me call this x1, okay, but this is maybe confusing, xk1 over here, let me put 1 over here, x1 k1, okay, first process k1 sample. So how about this? I'm selecting a sample at any time. So what do I see? I see, this w value, where it comes from a Gaussian distribution. So I see that x first process K1, its value is xk1, 1, let's say, okay? So this is a Gaussian distribution. So let me write it like this, n 0 sigma w square, like this one, okay? So how about this one? Again, first order PDF. This is, I think it's clear, Kate sample. This is Kate's K1, again K first, let's say, sample. So I have this second process sample like this. And what's the distribution of this? Let's select a sampling instant, maybe this instant. At this instant, what do I observe? I observe, you know, again a Gaussian distribution. And this is coming from, this is distributed symbol, this. Okay. How about this? First order description is done. Now, let's go and examine second order descriptions. Okay, again, let's divide this. Second order PDF description. Okay, so this is x1, this is x2. So how can I have this? Again, let me define something similar. First process, K first sample, K1, first process, K2 sample, and so on. Now I have these instances, let me say like this. Okay, so how can I express this? No, joint distribution. Actually, we have studied this before. This is nothing but, if I write this over here, this is the marginal density times the conditional density given the first sample, let's say. So this is the thing about predictability. K2, right? 1 given K1, 1. Okay? These are all 1. First process. So how about this? Now, I have already calculated this one. This is n0 sigma w square for all K1. How about this one? For the first process. So for the first process, if you know a value at a sampling time, you know the values at all times. Okay? So this is equal to, you know, a deterministic relation, delta. This is another time. This, I have something like that. So it is the product of these two, this density. Okay? So joint density, this is equal to this. Okay? This part is equal to, let me write it like this, it's equal to this. The reason is, if I know the value of this process at a particular time, process doesn't change, it stays fixed. Okay? So the value at, okay, K1 is equal to the value at K2 for the first process. Okay? Very good. Now, how about the other one? F x2 K1 x2 K2 this is this. Now for this process, if I know this sample, what can I say about the next one or the following one, etc.? Well, I cannot say anything because they're IID distributed. So actually that is even easier to understand, because from this IID distribution, I can write this as a product of two distributions. Where each one is Gaussian distribution. So let me, well, sometimes you need these arguments over here. So let me erase this. There is a notation also for this one. This is n, and this is the variable of the first distribution is this, x, k1, 1. You put a, sometimes this is used, a semicolon, okay? Let me erase. You put a semicolon, and you write the mean and the variance parameters of the distribution. So it's clear that this is a function of the first argument and a function of the second argument. Okay. So this becomes the expression. So for this one, again, this is n. The argument is this. This one is Gaussian distribution. Its variable is, as you see over here, 0 sigma square. Okay. This is the second one. So I'm multiplying two Gaussian distributions and I'm getting this joint density. The first distribution has this variable, the second distribution has the other variable, and they're identically distributed. They have the same expression, and that is it. Okay. So, you know, that is it. That is the end of this, but moment descriptions. So if you have PDF descriptions, moment description is even easier, because let me write this moment description over here. So what is this expected value of moment description? x1, k1. So this is the mean function. Let me write it over here, mean function. Well, this is the distribution, and its mean is always equal to 0. Okay. How about this one? Again, mean function. So moment descriptions are in red, let's say. The mean function, the first moment for the second distribution is also equal to, let me write a little better, also equal to, for all k, okay? For all, let's say k1 over here. This is, let me write k1 also for this one. For all k1. This is also valid for all k1, and so on. How about this one? You know, let me write this autocorrelation. So, what is this? Let me write the definition. If we are confused, because this will be a little bit more complicated. Rx1, k1, k2. Okay? X1 process, two samples. And their differences, you know, K1 minus K2 difference, okay? So this is xk1, xk2, I have conjugate, let's say it's complex valued. So I'm putting these conjugates also to emphasize that the second argument is conjugated, okay? Sometimes, you know, this is like a multiplication process, so by putting this conjugate, I can also say that this is my second argument, K2 argument, okay? Because otherwise it's like confusing. Sometimes conjugate can be used for that purpose. Now for this one, what do I have? Even though this is real valued, I can still use conjugates, as you see. So I have, from this process, K1 and K2 values, they are the same. So these two quantities are the same. So what do I have? The end result is expected value of x, let's say 1, k1, let's say magnitude square, because of this conjugate, even though it's real valued. These are all about x1. So this is, as you see this, the final result is. So this is the variance, because it is zero mean. Second moment is also the variance, okay? Well, how about the other one? Autocorrelation. Autocorrelation. Okay. So let me write this with black pen, black marker. K1, K2. Expected value of xk1, xk2, okay? So what should I do? Now I should calculate that expectation for this second process. this kind of a process. But what I know is that this sample and this sample, they are independent if K1 is not equal to K2, obviously. If they are the same, then it's the parentheses square. So let me write that. This is equal to when K1 is equal to K2, and when K1 is not equal to K2, I have the following expected value of second process sample square expected value. And this is, again, this is equal to, or let me write it over here with this kind of, this is equal to sigma w square. How about this? So this is expected value of, if samples are different, these indexes are different from each other, then expectation factorizes into 2. Sorry. So what do we know? Now this is 0, this is 0, so the end result is 0. So how can I compactly write this? This is equal to, well, let me write this, sigma w squared delta K1 minus K2. But be careful. Now I'm using a Dirac, not a Dirac delta, but Kronecker delta, okay? Because of this bracket. This is not a Dirac delta. This is a Kronecker delta, okay? So what do we see? Now we see the following. Well, autocorrelation is like that for the second process, and it's a zero mean process. So what do I see? I see the following. This second process is also a white noise process. Why do I say white noise process? Because if I go right now, this is a discrete time process. If I go one sample towards right or towards left, as you see, if K1 and K2, if they are not equal to each other, even if you are deviating one sample towards right or towards left, so the process becomes uncorrelated. Okay? Zero mean and uncorrelated. So the second process is called discrete time white noise process. So this is obviously discrete time, and this is a discrete time white noise process. And as you see, I don't have Dirac delta over here, because right now these are integers. K1, K2, they are integers. And if you have the same integers, I have this value, indexes. If you have different indexes, you have 0. So you are losing correlation information for different samples. Again, we have uncorrelated process. So how about the first one? So the first one is not a white noise, because you see that its correlation is constant. Okay? Its correlation is a fixed value. So let me write this as a comment. Let me erase this part. Let's say so, x2 of k is a discrete time white noise process. So you may consider that this is the sampled version of a continuous time white noise process, but there can be issues involved about the sampling process. But you may consider it like that, sampled version of continuous time white noise. And x1 of k is not a white noise process, since its correlation is, well, is constant, let's say. Is constant, i.e. not an impulse function. Just to remember, you know, this it's a constant value, but it is supposed to be either in discrete time or in continuous time an impulse function to be white noise. Okay? Okay, so this is our first example. So let's continue with our second example. Let me see. Example 2. So W1 of n is plus minus 1 IID with equal probability. So it takes a binary valued process, 1 or minus 1, and with equal probability for every sample we have this distribution in an independent way. Okay? W2 of n is n01. Let me write it like this. Element of 1 minus 1. This is distributed with Gaussian distribution. This is also IID for every n. Okay, for every index n. So as you see, again I have discrete time processes, W1 and W2. So the question is, find PDF/moment characterization. Characterizations of these two processes. It's almost like the same problem. So I should again do a sketch. W1 of first process, W2 of n. Okay. So what do I understand from this description? Well, I see the following. So this process is taking two values, 1 or minus 1. So this is one of the realizations, as you see. So they're equally likely, and it goes like this. Another realization is, the red one, 1, 1, minus 1, 1. I think it's clear. So it of course goes the other way. So on. So there is maybe a coin flip. At every time you do a coin flip, at every time index 0, 1, 2, minus 1, etc. and you decide on the process value. So the other one is like the earlier process. So you are selecting something from a Gaussian distribution at every time instant. Okay. But this is a zero mean process. It goes like this. The second realization, another color as you see, it can be something like that. I'm just making up these drawings as you see. Let me erase this. Okay. So where is the axis? Axis is over here, and 1, 2, 3, minus 1, minus 2. I think it's clear. So this is the type of process that we would like to understand. Actually, this step is quite important. If you don't understand, if you sketch this wrongly, all of this calculation will be wrong. Okay? Well, let's continue. So W1 of n and W2 of n. So first order PDF. So how can I explain this one? So this is W1, sample K1, W1, let's say K1, I think it's clear. This is for W1, okay? WK1. So what is this distribution? Well, at any sample, so it's like 1 over 2 delta x minus 1, 1 over 2 delta x plus 1. Well, what kind of impulse symbol is this? Is this continuous or discrete? Well, this time, this is the Dirac delta. Because what I have is, I would like to sketch this distribution, isn't it? This is my distribution. Okay, it can be also probability mass, but this is a probability distribution, as you see. Let me see. WK1, So this weight is 1/2, and this weight is, location is 1, location is -1, again weight is 1/2. Okay. Actually, this can be both, you know, Kronecker delta or Dirac delta. But if I have selected, let's say, 1/2 for this, I could have done it at the beginning. Then this would be 1/2, and clearly this would be at 1/2. Then this cannot be Kronecker delta, because 1/2, in Kronecker delta, you have only integers, okay, as the argument. Okay, that is it. Now, how about the other one? The other one is WK1, second process at K1. Well, it's Gaussian distribution, isn't it? N01. Okay. Let me indicate the variable also. WK1, 01. Okay. Now, second order PDF. Second order PDF, FW1, K1, W1, K2, WK1, WK2. Okay, so what should I write for this one? Well, now these samples are IID, meaning that this is the product of these two distributions. WK1, F, W1, K2, WK2. So I have, oh, let me change this X, sorry, this is, let me write WK1, WK1 for this one. So as you see, this is this function, and I have the same function. Only difference is that now this independent variable is changed to WK2 instead of WK1. Okay, that is it, because they are independent. For this one, well, it is the same actually. I'm writing exactly the same, because again they are IID. This is WK1. Okay, because they are IID. So what do I mean by this? This one is Gaussian distribution. This one is also a Gaussian distribution, but different, you know, because as I have said, this first order description is valid for all K1. Again, this is valid for all K1, not a particular time. So at another time, it has the same distribution. So for the second order one, we take the product of these two. Okay. Well, moment description. Moment description, mean function. So what is the mean value of, where is the distribution? First order distribution is over here. What is its mean value? Well, expected value of W1K is equal to 0. How about the mean value of this? Expected value of W2K is also equal to 0, and of course for all K. Okay. Autocorrelation function. Rx K1, K2. As you see, whenever I have integers as the indexes, I'm using the square brackets. Okay? This is the signal processing practice in general. So this is equal to, well, I'm writing it a little, so not X, this is W1. W1, K1, because they are IID, that is, they are independent, W1, K2, and this is 0, 0. So this is equal to 0 when K1 is not equal to K2, Okay, that is it. Or, okay, and when k, okay, let me write it over here. When k1 is equal to k2, this is w1 square. So this is the square of this quantity, expected value, but if you take the square, you always get 1. So this is equal to 1. So this is equal to 0, this is equal to 1, and so on. Okay? So I have done this a little bit faster than usual, but I think it's clear. Okay. So this is our W2, K1, K2. This is expected value of W2. This, and again, we have the exact same result. This one. It is equal to 0 and 1 when K1 is not equal to K2. When K1 is equal to K2, this is just, W2 square, expected value. K1 is equal to K2, W2 parentheses square, and it has unit variance. This is this unit variance, and exactly the same. So what we see is that moment descriptions are exactly the same. So this is, both of them are stationary white noise, okay? Because both of them are zero mean, and they have impulsive, let's say, autocorrelations, as you see, okay? So you cannot predict one leg from the other leg, or one sample from the other sample, okay, of this process, because they're uncorrelated. So let me write that as a comment. Both W1, W2 of n are discrete time white noise processes. Okay, but it should be clear that process outcomes are wildly different from each other. Hence, one more time, we see that moments only give us a partial description. This is the reason that they are called sometimes partial descriptors. Okay? Partial gives us a partial description. So what do I mean by this partial description? So according to moment description, both of these processes are under the category of white noise. Okay? W1, W2. But if you see this one, it's a binary valued process, either 1 or -1. This is taking all possible real quantities as outcomes, okay? So they are, you may say, quite different type of processes. So it's not possible to identify any difference in terms of this description. So sometimes you can see in some cases, it says that we have, well, in some, let's say, discussions, AWGN, shorthand, or let's say acronym, is used to state that, let's say not state, but to stand for additive white Gaussian noise process. Okay. So additive part is, something else. You are just adding this to another process, let's say. But white Gaussian noise process. So for a Gaussian process, what we need is mean function and the covariance function, isn't it? We have described this. For the nth order PDF description, if you know the mean function and the covariance function, then you are done. But if you say white, well, white information is just the mean function and the correlation function, as you see. Okay, you are done. So when you talk about white WGN, white Gaussian noise, it's something like that. Okay. So this additive part it is just saying that maybe you have a signal like this. Let's say y of n there is a desired signal s of n plus w of n, and this part becomes AWGN. Okay. AWGN, additive white Gaussian noise. Additive part is this. Sometimes noises can be multiplicative, but this is the additive part, additive white Gaussian noise. Okay. So we will continue after a mini break. Okay, thank you.